Recording's rolling. It's Monday, October 20. Starting a new module 4. So lesson 401, polynomial functions. So module 4 is all about polynomials. So module 3, you guys remember, was all quadratics, there were a bunch of parabolas. So you saw a bunch of x squared, plus blah blah blah. Okay. So this is, well, what if we take x to higher powers, like x to the 5 or x to the 4, or x to the 3, something like that. Okay, so polynomials, you're looking for just a whole number of powers on x. So here's an example. We got 2x to the 4 minus 3x to the 3 minus 4x squared minus 5x plus 6. Right? Did you guys notice that it's all whole number of powers of x? Right? And notice there's no fractions of x. So there's no like, here. I know there's some counterexamples somewhere in here. Well, if you saw something like right here, you guys see, okay, 2r minus r squared, that's a good start, but then plus 1 over r squared, that would not be a polynomial. So anytime you see something like that, then it's kind of dead. You don't have to worry about it for this module. They mostly just want you to recognize that that is not a polynomial. Right? Of course, any of these you could always graph by plugging into Desmos, but I want to show you guys some things about the graphs. Okay, so right on the very first page on 401, they show you some categories of end behavior. So if you have, well, if you look at the highest power on x, like if x to the 4, if that's your biggest term, something with x to the 4, right, then as long as it has a positive leading coefficient, then it will always bend up like this, just like parabolas did. Right? You guys remember with parabolas, you might have like y equals x squared plus 3x plus 5, something like that. Right? So those also bend up like this, didn't they? So what it says is it goes up to the left forever and up to the right forever. So in a way to spell that out mathematically, to say as x approaches negative infinity, let's say if you're going to the left, f of x, that's like your y value, approaches infinity. That's what this arm says right here. And if you go to the right forever, as f of x approaches positive infinity, so you're going to the right forever, then f of x, the y value, also approaches infinity, but that's in the y direction, so it goes up forever. So up to the right. Okay. Now, if you throw in a negative leading coefficient, so if you have y equals negative x to the power of 4 plus blah, 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 bunch of smaller stuff, then it'll always bend down like this. So you can go to the left and down forever, or to the right and down forever. Now, if you have, if the degree is odd, let's say if the highest power of x is like 1, 3, 5, 7, 9, something like that. So x to the 7 plus blah, 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 and a bunch of smaller stuff. And you have a positive leading coefficient, it'll always go up and to the right forever and down to the left forever. So a classic example, actually they're pointing out the very basic one. It's just y equals x to the 5, right? Which looks a lot like y equals x to the 3, just the basic shape. You guys know y equals x to the 1 or y equals x would just be a straight line. Again, it goes up to the right forever, down to the left forever. Okay? Finally, if you have the same scenario except a negative leading coefficient, so you go like y equals negative x to the 3. That's what they're showing right here. You just turn the whole thing upside down, and now you can go up to the left forever and down to the right forever. Yeah, there's a way to spell that out mathematically. Right? As x goes towards infinity, y goes to negative infinity, that's down to the right. Or something like that. Let's get that. All right. So, yeah, let's do. There's a counterexample I was looking for. Okay. So it starts out like a polynomial, right? 11x to the 3 plus 5x squared minus 7x. And I was almost going to do this one as an example, but then we ran to this one, minus 6 over x. Guys, when you see this right here, minus 6 over x, does that create like a vertical asymptote? Can x be equal to 0? Because what is 6 divided by 0? Huh? Let me try it out. What's 6 divided by 0? What's my calculator going to say? Error. Can't divide by 0. Okay? So on a graph, this would show up as a vertical asymptote. Okay? Right, let me do this. I'm going to pull this up on Desmos and show you guys exactly what I'm talking about. Desmos. I'll type that expression into this graphing calculator, and I'll show you that there is a vertical asymptote, and then I'll show you guys a classic polynomial. I'll show you guys how to graph some of these. Okay? And so it says y equals 11x to the 3. So y equals 11x to the 3 plus 5x squared is 5x squared minus 7x. Okay. So far that's a polynomial. But this last part, minus 6 over, whoops, x minus 6 over x. Okay. So that all I did was I took that expression right there. I just plugged it into Desmos. Okay. And well, can you guys kind of see there's going to be a vertical asymptote on the y-axis? Okay. So x cannot be equal to 0. Now, if I, whoops, meant to do this. Zoom out. Okay. Okay. It's just a wacky looking function. Okay. What if I do this though? What if I get rid of this, this right here? Okay. That looks probably more like reasonable for like a high school question, doesn't it? Or something like that. Like if I asked you guys to graph that, could you come up with this? I'll show you exactly how. No, just like the last quiz or any assignment, I'll give you like some like if I give you this equation and I give you a graph, it's going to frame it so that you can graph it nicely on whatever graph I give you. Like on your last quiz, the graph I had you guys do, it was definitely framed between -5 and 5, so it wouldn't take too long to kind of hunt around, even if you didn't know how to find the vertex, right? You could just start plotting points, right? Now, I definitely want to do this with you guys because so many guys got the graph in the last quiz, and so many guys didn't know how to plot XY points, right? So I'll show that here, right? And I'll show you guys it'll be the same thing. Right, so let's go over here. So I'm going to do f of x equals, and I'll copy down most of this. I'll just ignore that last term right there. Let's go 11x to the 3. So we have some kind of polynomial. Plus 5x to the 2 minus 7x. Let's say just end it right there. So that's the polynomial. Okay. Right. Now, if I go back to these rules I was telling you guys about before, the fact that the degree, guys, what would the degree of this polynomial be? What's the degree? It's the highest power, which is what? 3. Yeah, 3. Right. Right. So that which is odd. So it's basically going to look like this: up to the right forever, down to the left forever. Combined actually with this detail. Isn't the leading coefficient positive? I mean, it's positive 11, but the fact that it's positive, it'll go up to the right forever and down to the left forever. Okay? Now let's pick some points and solve this out. So I can set up an xy table. XY table, different value for x, different value for y. Okay. Now, kind of working from decimal. Let's go. How detailed should I get this? Let me check. Okay, glance back here real fast. Let's go by half values. Right. So I think that just makes more sense for how this particular one would be framed. So let's go -1.5, -1, -0.5, 0, 0.5, 1, 1.5. Okay, I think that'll create enough of the graph. We're getting an idea. Okay? And I'll show you guys the same calculator trick that I've been doing for a while in front of you guys, okay? Which is everywhere I see an X in this model calculator, which everybody has, I'm going to put in an answer. So watch this. 11 answer to the power of 3. Okay? And that answer takes the place of x, just like we've been doing for the last few weeks anyway. Okay? Plus 5x squared minus 7x. Boom. Okay. Now, the first answer is jump. Doesn't mean anything. But I can plug in these x values one at a time. So if I plug in -1.5, so -1.5, I hit enter. Okay, now the calculator's thinking, okay, something about -1.5. I scroll up, plug it in that expression, gives me -15 point something. So here I'm going to round a little bit. -15.4-ish. That's not exactly it, but that's pretty close to -15.4. Okay. Then if I plug in -1, plug that into the expression, I get exactly 1. If I plug in -0.5, plug that in, I get 3.4-ish. Again, rounding a little bit. If I plug in 0, I do get 0, and that makes sense because all three of these terms do have x in them. So 0, 0 has to be a point. If I plug in 0 for x, it has to come up 0. If I plug in 0.5 to that expression, I get negative point. I'm rounding to the nearest 10th place. It's pretty close to that. If I plug in 1, I get 9 exactly. And 1.5, okay, I'm getting like 38 about, well, I'll do 37.9, rounding to the nearest 10th. Okay, so those are rounded to the nearest 10th, but that'll be plenty enough to tell you exactly what the basic shape of this graph looks like. Okay? So I got x-axis here, y-axis here. Let's go -1, -2, 1, 2. So -2, -1, 0, 1, 2. Okay, that's the entire domain of options that I plugged in here. Yeah, hang on. Yeah. Hold on. Hey guys, I'll be right back. All right, we're back recording. All right, so what I did, okay, catch it here. All right, I have this polynomial. Okay. I made an xy table. I plugged in a bunch of x values into this calculator. It gave me all the corresponding y values. Now all I have to do is plot the points. Now, I do see that the highest y values, it's getting pretty close to 40. So let me scale this 10, 20, 30, 40. 10, 20, 30, 40. Same thing the other way. We go -10, -20, -30, something like that. Right. Okay, so all the points will fit here. Okay? I did squash y axis a little bit, but it'll give the same basic shape that I need. Okay? So I see 0, 0 as a point. You got to plot that point. I see -1.5 and then -15. That's right about here. -1, 1, which is right here. Because remember, this goes up to 10, so that's fine. Okay. 0, 0. Oh, -0.5, 3.4 is probably right here. It's 0, 0. 0.5, -0.9, 1, 9, and then 1.5, 37 is getting close to 40. Let's wait here. Okay. So if I connect all the points, yeah, look at that. It does basically this shape. And then it'll go forever to the right, forever up, and forever to the left, forever down. Yeah, right. Which exactly matches the rules that your Locus balance sheet. Right? When you have an odd power for the for the degree, right? An odd degree, something like that. Right? And x to the cube. Whenever you have x to the cube in a larger polynomial, yeah, okay, that's your degree. Right? It can look like that. Right? Up to the right, down left, and maybe some little sneaky shape in the middle. That's all. Right? And so these are pretty much all like that. They just follow those. Now there's some fun word questions too. Of course, I know this is really abstract because we got like x's and y's. Right? So what's some applications of this? Right? So they give like the density of the sun in grams per cubic centimeter as a function of distance from the center, like, proportional to its radius. That one's fun. This one I thought was interesting. This one I put on the main video, so to go through them more slowly. Right? The number of triangles you can create by some number of dots that are not collinear. Right? There's this expression they give right here. So that one's fun. Um, there's so you drilled it for a cone. What other word puzzle did? Okay, the last one I did in the main recorded video is there's some box that's 10 by 10 by 4, so 10 centimeters by 10 centimeters by 4 centimeters. Okay, and then they're gonna change the dimensions, so they're gonna make it taller, but also shorter and okay. So they're taking each of the sides and they're subtracting x, and they're also making it taller by some value 2x at a time. So you can set up the expression. Actually, you know what? I have it right here. I have it right here. So here's my 10 by 10 by 4 box. Okay? And then we're shrinking the sides by some value x, and we're also growing the box by 2x tall. Right? So you get width is 10 minus x, 10 minus x, and then the height is the original 4 plus 2x. Right? So you can expand this out. You can FOIL this bit out here. Right? So it looks like this, and then multiply this. So it's like a super FOIL. It creates a crazy looking polynomial, which if you clean it up, actually ends up looking like this at the end. Okay? And so keep that in mind too. Sometimes they start out looking factored form, but if you want it to look standard form, you can just do a bunch of foiling until you get to standard form. Okay? And then from this point of view, okay, here's the volume of some box that you can put anything in for x. Right? So you get a box that looks like this. Okay? Notice this has a power of 3 is the highest power. Right? Is that right here? Power 3. Right? So it has a degree of 3. Right? So probably okay. And the question they asked is like, what's the largest volume box that you can make? So there's different ways to actually get that. One way is you could actually plot this function, say on Desmos or graphing calculator, and just say, oh, where is the largest volume? Something like that. Okay. Another way, and you can do that, and it comes out where x equals 2. That would maximize the volume of the box, and the maximum volume ends up being 512 cubic centimeters, right? Which creates a perfect like square type box, 8 by 8 by 8. Okay? There is actually a way to solve this also the calculus where you take the rate change and set the rate change equals 0. It gives you the same answer. So that 2 there, you can also get which goes around. Right? So that's a fun word application of all these polynomials. All right, so just like normal, I will give you guys time. You can watch the full video. I'll play the full video in the background. Right, so you guys can watch that. Watch it at your own pace. If you want to open Alex, you can. The next Alex assignment, here, let me write this right here. Alex, I opened up 4.1, 4.2 we'll do tomorrow, and 4.3 we'll do the day after. Okay, that is due Friday. All right, and if you want to hop in that and start working there, then I can walk around and check on you guys and help you out.